Hello, everyone. So first of all, I would like to thank Plia for the opportunity of being here today. The paper I'm presenting you today is called Designing and Building for Extreme Environments, a Multi-Criteria Decision Model to Evaluate Architecture for Extreme Temperatures. First, I would like to describe to you what is an extreme environment. An extreme environment is characterized by very extreme physical conditions that make human life very hard or even impossible. These are conditions such as temperature, acidity, radiation, desiccation, pressure, heavy rainfall, salinity, and air quality. The two chosen climates for the study were Yakutsk in Russia, where the lowest ever recorded temperature was minus 64 degrees Celsius, and Needles in California, USA, where the highest ever recorded temperature was 52 degrees Celsius. Now, what is important when building for extreme environments? Literature tells us that it's three main things: building morphology, materials, and interior spatial configuration. The first one will be accessed by form factor, which defines the compactability of a form. The second one will be retrieved from the material libraries from Energy Plus, and the third one will be achieved from the guidelines of NASA. Secondly, what is a multi-criteria decision analysis model? An MCDA is a framework where I have a goal, which in this case is evaluate architecture for extreme environments. I then give the software criteria, which we will speak afterwards about. I then populate my model with options, which are the construction assemblies with the four main materials that we spoke of before. I will then give weight to my criteria, which will allow me to create scenarios so I can give different criteria, different weights in order to assess different things, which will then give me results that I can analyze later on. Speaking of our criteria, the first one is energy efficiency. This was achieved through designing the model of the prism in Rhino, then importing it into Grasshopper, and communicating with Energy Plus with Honeybee and Ladybug. So in order to conduct the simulations, we needed to give a series of inputs to the software, such as space usage, occupancy schedules, lighting conditions, and equipment load, which mainly refers to electronic equipment. All of this will give us the free-floating interior temperature of our prism. But in order to access energy waste to heat or cool down our prism, we also gave the software comfort interior temperatures from 16 to 18 degrees Celsius on Yakutsk and 26 to 28 degrees Celsius in Needles. And the outputs of this simulation were our free-floating interior temperature and our energy consumption that was achieved through giving the program comfort interior temperatures. Our second criteria, material performance, was created with 5 criterion: surface temperature, material fracture toughness, weight, carbon footprint, and end of life. For our third criteria, architecture performance, we took the guidelines from NASA and their example of a human habitat for other planets and designed one that will be applicable here on Earth, with these characteristics, but still respecting the guidelines of spatial organizations. As it is, it always rated high on our models because it followed all of the guidelines. Lastly, circularity exists as a criteria that englobes others in order to assess environmental impact. Next, we will be looking into the construction assemblies, which are the options that we input into our model. So we gave our model 4 options based off the materials that we spoke of before. These construction assemblies were retrieved from the Energy Plus material library, and the correct materials for each climate zone were used. So basically the materials for climate zone 2, which is Needles, were used, and the materials for climate zone 8, which is Yakutsk, were used. This means that the materials from climate zone 2, which is Needles, have much less insulation, for example, than the ones from climate zone 8, so they're adapted to their climates. These tables show how these options perform on all of the criteria mentioned above, which are there represented on the left. Now, the next step is to weight our criteria and create scenarios. So on the left, we have our criteria, and above we have all of our models or scenarios. For model A, all criteria were given equal importance, 25%, creating thus our base model. For model B, European energetic standards were used as optimal values instead of just the highest and lowest score of the proposed construction assemblies. For model C, more importance was given to energy consumption, service temperature, carbon footprint, and end of life in order to create a model to assess environmental impact. And for model D, more importance was given to service temperature, weight, and fracture toughness in order to assess the transportability of our options. In both of these models, circularity was removed because it became redundant, and the criterion for free floating temperature was also removed because the difference were very, very low, so it made no sense to keep it. Finally, our results. Here in these tables, you can see how well our options and our construction assemblies rated in the 4 models. So you have the models presented above and our options presented in the left. The assembly that rated the highest in needles on all the models was metal. In Yakutsk, it was wood and metal, with mostly similar percentages. The second best rated in needles was wood, and in Yakutsk, it was both metal and wood. This was particularly interesting for us because it suggests that a similar construction assembly can be considered for 2 very different and very extreme climates. As you can see, both generic and mass materials rated much worse than the other 2 if we compare percentages. I would like to thank you all very much for listening to me and to wish a good conference to all of you.